3.1 The Diode Theory. In this chapter, there are 11 sessions. 3.1, that's the basic ideas of diodes. 3.2, we're going to discuss the ideal diode. 3.3, that's the second approximation. 3.4 is the third approximation. And section 5, we have troubleshooting, followed by reading a datasheet for a diode, and then how to calculate the buck resistance, the DC resistance of a diode, load lines, surface mounting diodes. Section 11 is the introduction to electronic systems. There are many sessions, but not all sessions are very important for our class. 3.1 The basic ideas. And then we're going to talk about the diode, the terms for diodes, the symbol of diode, and then a few examples, some diode circuits, and then a curve called a diode curve that can show the behavior, the characteristic of a diode. And then we're going to talk about the power dissipation, also the bulk resistance of a diode. The electronics devices can be categorized into linear or non-linear devices. Linear devices can be resistor. If you draw a graph, shows the current versus voltage is a straight line. And there are non-linear devices, and the diode is one of them. The current versus voltage of a diode is non-linear, is curved. This makes it much harder to learn diode than learning ordinary resistor. Here shows the symbols for diodes. The one on the left called the case diode. It shows two boxes. Two boxes are adjacent to each other. One box shows the letter P, which means this is a positive type material. The other box has a letter N, and it means it's a N-type material. The diode with the P-type material has a special name called anode, and then the N-side material called cathode. On the other side is the schematic symbol of the diode. It's a triangle with a bar attached to it. The bar represents the cathode, which means negative side. The flat side of the triangle is the positive side, therefore is the anode. Between these symbols, the schematic symbol is the one we use the most. Here we compare the schematic symbol of the diode with a real diode. They are in the same orientation. The triangle of the schematic symbol is the main body of the actual diode, and the bar of the schematic symbol is the strip of the actual diode. So the actual diode has a mark or a strip. It represents the cathode, the negative side of the diode. And then the other side, the opposite side with no strip, is the anode, the positive side of the diode. You may ask, what's the reason of using a diode? The key purpose for using a diode is to direct current, is to bypass current. Currents only can flow in one way, from positive towards negative, from anode to cathode. And there is no way for the current to flow in the reverse direction. The diode will block the current. Now we put the case diode, the schematic symbol, and an actual diode together. I also put a quarter coin next to the actual diode to see the relative size. Here we put a few diodes, such as the GaN diode, photodiodes, laser diode, PN diode, and the LED diodes. They are used for remote control, lasers, laser pointers. LiDAR, which is the laser radar for scanning, measure the distance, and then ring laser gyroscope for measure the roll yaw pitch for missiles or airplanes. Here we have additional diodes, such as the varactor diodes, and this diode acts as a voltage-controlled capacitor when operated in the reverse bias. Some application can be electronics tuning circuits, including the voltage-controlled oscillators, phase lock loops, the FM modulators, RF filters, radio or TV tuning circuits. We also have the vacuum diodes, Zener diode, tunnel diode, and the Schottky diodes. In our class, we're going to spend some time learning the LED diodes, Schottky diode, and also the Zener diode. To learn how diodes works, how about let's put the diode in a circuit. This is the basic diode circuit, and there's no other circuits that works and that can be easier than this. Remember to put a resistor in a circuit, otherwise when the diode start working, bypassing current, it becomes a short circuit. So the circuit is made of a power source, Vs, a resistor, specifically this is a current limiting resistor, and then a diode. The current is represented using the arrow. The current flows upward on the left side and then make a right turn, flows from left towards right, and then go through the diode from its anode to cathode. Vd represents the voltage drops on the diode. And we can say the diode is in the forward bias, which means current can flow through it. It conducts current. If you flip the diode is no longer conducting current. It blocks current from flowing. And we can say that the diode is in the reverse bias. If we measure the voltage and the current that flow through diodes, including forward bias and the reverse bias, let's plot all the points we measured. This is the curve. And then in the horizontal axis, that shows the voltage drops on the diode. And then in the vertical axis, the ID represents the current goes through the diode at any particular voltage. This is called the IV graph, the current voltage graph. We can see that the relationship between the current and the voltage for a diode is not linear. It's a curve. And the more interesting thing is that at the beginning, if there's no voltage, no current, and if we add a little bit voltage, the current increases quickly. And then if we add just a tiny bit more voltage, current increase rapidly. Shoot to the moon. This is a very important feature for diode. And there is a special voltage for that turning point. And this is the 0.7 volt. It's so special, and we give that a special name. We call it knee voltage. It's like the knee of the leg. It's a turning point. It's a pivot point. We can also say that this is the activation voltage when the diode is activated and fully functioning, can bypass lots of current just by adding a little bit more voltage than this. Please remember this number. I strongly recommend you also put this number in the cheat sheet. We're going to use this number in this class throughout the semester. Not all diodes have the same knee voltage. Some diodes has a little bit less, some diodes have a little bit higher than 0.7 volts. For most of the problem we are solving, we use the 0.7 volts. The 0.7 volt is for generic diodes. In other words, when we solve a problem, unless specified, otherwise we will use 0.7 volt, this default voltage. One analogy of the diode is like a switch. If the switch is off, no current can flow through it. And then in order to turn on the light or turn on motors, turn on computers, turn on the circuit, you can simply flip the switch. You need to provide a small force to touch the switch and then flip it to turn this on. That force required to toggle the switch is the 0.7 volt Dani voltage. Now let's spend more time learning this very important curve. And we're gonna break it down, partition it, and learn different regions. This region, the curve is on the right-hand side of the vertical line and is to the right of the 0 volt, is called the forward region. This is when the diode can conduct current. We put a mark here that represents the minimum voltage to activate the diode. Dani voltage equals to 0.7 volt. Now we also put the other side of the curve here. This is when the diode is placed in the reverse direction. So it blocks current. No current can flow through it, in theory. However, in reality, there are very few amount of electrons can go through it. This is the reason there's a small gap between the horizontal line and the curve. For the little current that goes through it, we call it reverse current. It represents very small amount of current can go through it until it just drops rapidly. This is when loss of current goes through it, and then it breaks the diode. It burns the diode. And this is the time you see the smoke come out. Now let's put all the pieces together with the key terms. P and N regions are the two separate pieces of semiconductor. Each piece has resistance. After the barrier potential is overcome, all that impedes the current is the ohmic resistance of the P and the N regions. The Buck resistance of a diode is defined as the sum of ohmic resistance of N and P materials. The formula is the Buck resistance RB equals to RP plus RN. The Buck resistance depends on the size of N and P regions and how they heavily doped. For most diodes, the Buck resistance is less than 1 ohm. If the current in a diode is too large, the excessive heat can destroy the diode. For this reason, a manufacturer's datasheet specifies the maximum current a diode can safely handle without shortening its life or degrading its characteristics. The maximum forward current is one of the maximum rating given on the datasheet. These current may be listed as Imax, Ifmax, where F stands for forwarding, IO, or etc., depending on the manufacturer. For instance, a 1N456 has a maximum forward current rating of 135 milliamps. This means it can safely handle a continuous forward current of 135 milliamps. You can calculate the power dissipation of a diode the same way you do for the resistor. We are using the same formula, that's power equals to voltage times current. But over here is for the diode power. We use the symbol PD to represent the diode power equals to the voltage across the diode and the current passing through the diode. The power rating is the maximum power the diode can safely handle without shortening its life or degrading its properties. The symbol is Pmax and equals to the maximum voltage Vmax times the maximum current Imax. Example 1. Find the maximum forward current of 1N46 diode. This we need to use the datasheet of the 1N456. In the datasheet, we find out that for 1N456 has a maximum forward current rating of 135 milliamps. This means that it can safely handle a continuous forward current of 135 milliamps.